All right, so in the previous video, we saw about the linear model with only one predictor. We saw what it looks like, how to fit the model given some training data, and then have an idea of what to look into in order to diagnose whether the model is good or not. Now we're going to start adding more predictors into the model. So we're going to go from a simple linear model to a multiple linear model. And in particular, let's say we have p predictors from x1 to xp. Now, what does the model look like? Again, we have beta 0, which is the intercept. And now we have one coefficient per independent variable. So for x1, we have beta 1. For x2, we have beta 2. And all the way up to beta p for xp. And so beta 0 is still the overall intercept. So what is the value of y when x1 equal x2 equal everything, xp equals 0? So when everything else equals 0, what's the value of the response? And then these betas are still slopes. They are slopes in a hyperplane. We're going to see an example now. And what they're telling us is what is the average effect on y of having a unit increase in the specific coefficient. So if we increase, let's say, x2 by 1 unit, what is the average effect on the response, maintaining everything else fixed, maintaining all the x1, x3, x4, etc. fixed at the same value. And so this links back to what we saw in the previous videos of everything else being equal. So what this is assuming is if nothing else changes and we just increase 1 unit or decrease 1 unit in this specific variable, what's going to happen to the response? And the problem now is that to properly interpret the model is going to be more complicated. It's going to be more difficult because we are going to see it's not so easy to really know what's going to happen to the response when we have a change in one variable or the other, because everything is going to depend on the other variables. So anyway, what does the model look like? The simple linear model we saw, it was just a straight line, something like that. When we have more independent variables, what are we looking at? Well, we're looking at a plane or a hyperplane. So in this case, we have the relationship between two predictors, x1 and x2, on the response y. So what we're looking at is a plane. So for any given observation, let's say this one here, we have a certain value for x1, a certain value for x2, and we have a certain value for the response over there. So we are looking at a plane. Where are the coefficients here? Well, again, this length over here would be beta 0. And then we have a slope for each of the two independent variables. So if we look at x1 over here, this slope is what beta 1 is telling us. And if we look into the other direction, over here parallel to x2, this is what beta 2 is measuring. So it's again a slope of this plane in this three-dimensional space. So how do we interpret the coefficients? Okay, let's say we go back to the example in which we're looking into the sales of a certain product by the amount spent on advertising on TV, radio, and newspaper. So we have now 3 independent variables, TV, radio, and newspaper. The model would look like sales, the dependent variable, equals beta 0, the overall intercept, plus beta 1 times TV, beta 2 times radio, beta 3 times newspaper. How do we interpret the intercept here? Well, it would be the amount we sell if we don't advertise anything on TV or radio or newspaper. So if we don't advertise anything, how much will we sell anyway? Let's say we got our data, we feed the model through OLS. What do we get? Well, here is the example. Our estimated model would be almost 3 for the intercept, plus 0.046 for TV, plus 0.19 for radio, minus 0.001 for newspaper. And now this is interesting because this is saying something like the newspaper have a negative effect. So the more we advertise on the newspaper, then the lower the score of the response. Now, this doesn't make a lot of sense, right? We could interpret this as the newspaper ads have a negative effect on the sales. Now, is that correct? Well, no, that's not a proper interpretation, because if we look at the relationship between sales and newspaper alone, without TV or radio, we see here that there seems to be this positive correlation. So this is not saying that newspaper have a negative effect on the response. What this is saying is, once we have the TV and the radio in the model, if we look into the newspaper, it's going to allow us to kind of correct the estimate provided by TV and radio. That doesn't mean that newspaper on its own has a negative effect on the response. It means that if we are already accounting for TV and radio and their effect on the response, the newspaper will have a negative effect on the estimate given already by TV and radio. It's a little bit more involved than just looking at the number. Let's actually compare a simple and a multiple linear model. So we saw that adding radio and newspaper produces a very different model. So if we only look at the TV, what we saw in the previous video, this is our table, these are our estimates. If we include multiple predictors, these are our estimates. So we see that the effect of the TV remains more or less the same. And now we have this positive effect of radio that appears to be the largest, and this apparently negative effect of the newspaper. And what we see is also that the intercept changes a lot. So by modeling only the effect of TV, we saw that with no advertising, we would sell about 7 units. Now, what we see is that if we don't advertise on TV or radio or newspaper, we would sell like only 3 units. So what this is saying, or what we can get from these results, is that in this first model, the 7 units were already accounting for some of the advertising on radio or newspaper. So it's not that we sell 7 units if we don't advertise TV. It's that, well, for those values of the advertising, we were anyway advertising radio and newspaper probably. So that's what we are observing there, the difference between these two coefficients. Anyway, the thing is that the complex model, the one with the 3 predictors, reduces the RMSE from 3.2 to 1.7. So it's a much better model in terms of how well it makes predictions of sales given only TV or given TV, radio, and newspaper. And in fact, the R-square, telling us how well the model explains all the variability in the response, goes up from 0.61 to 0.9. So this second model would be able to explain about 90% of the total variability we have in the sales variable. So it's a much better model from that point of view. And at this point, we might wonder, what is the benefit of having more than one predictor? Well, we do it essentially for one of 3 reasons. The first reason is, well, simply to have better predictions. Let's say we have a simple model, F1, that depends on up to P predictors, and with it we can compute estimates of the response. Now, let's say that the residuals of those estimates are E1, so the residuals for the first model. Let's compare that with a more complex model, F2, in which we have the same P predictors plus another one. So let's make the model a little bit more complicated by adding one more predictor. Again, we can make estimates with this second model, and those will have residuals E2. Now, the point is that, generally speaking, the residuals E2 are smaller than residuals E1, or at worst, they're going to be equal, meaning the predictions from the second model are going to be more accurate. So the second model is going to make better predictions than the first one if we add a new predictor. The second reason is simply to control for factors other than the one of interest. So let's say we're carrying out a specific study, we have a certain hypothesis that we want to test, and in particular that is about the effect of a certain X on the response, certain factor X. But we know there are other factors that affect the response at the same time. So what we have to do is remove their effect when studying the effect of X. So again, using the example of the surgical procedure, let's say the surgical procedure is we want to study the X, and then the days to recover is the Y. But we want to study this effect regardless of the surgeon or the patient's age. So we have to control for the surgeon and the patient's age when we want to see what is the effect of the surgical procedure on days to recover. And then the third reason is very related to it, and that is to model interactions among factors. So let's say that the effect of X on Y depends on a third variable. There is an interaction effect, and we need to model that interaction explicitly if we want to really see what is the effect of X or X and the other variable that it interacts with. So for example, let's say that the effect of the procedure is different between men and women. So we need to explicitly add the sex of the patient into the model in order to control for this interaction between the procedure and the sex. And so everything relates back to this picture we've been having all along about a comprehensive study, in which we want to see what is the effect of these controllable factors on the response, but we want to do it by controlling for all the other factors in here and partially other factors that might be in there, but that are not of interest. So all the time the question is, what is the effect of the factors of interest? Let's say they're these ones, while controlling for other effects, whether we can control them in the experiment or not. So let's take a more detailed look into this. What does controlling for other factors really mean? Say we have some factor x1 that is of interest. We want to measure the effect of this x1 on the response, but we want to do it while controlling for some other factor x2. So in a sense, we want to remove the confounding due to x2 when looking for the relationship between x1 and y. We could do it in a simple way by fitting two simple linear models. The first one would be about estimating x1 based on x2. That's it. The residual of this model, let's call it R, would be the difference between the true x1 and the estimated x1. So by construction, these residuals are the part of x1 that is uncorrelated with x2. And then we can get those residuals and use them in a second model to try and estimate the response. And so this first coefficient, gamma 1, would measure precisely the partial effect of x1 while holding x2 constant, because we precisely took out the correlation between x1 and x2 here in this residual. And so gamma 1 is precisely measuring what we want, the partial effect of x1 holding x2 equal. Now, alternatively, we could just fit the multiple linear model of y given x1 and x2. And it turns out that this coefficient we will have for x1 is precisely the same as gamma 1, which is what we are after, the effect of interest. So we could see that by fitting directly the multiple linear model, the effect of beta 1 would be exactly the same that we would get from gamma 1 after partialing out the effect of x2. And so this is why the coefficient interpretations require this everything else being equal. This is precisely what we want. If we want to see the effect of x1 on the response while controlling for x2, precisely the linear model is giving us that effect when looking at beta 1. So, okay, let's take a look at the accuracy of the model. Everything we saw in the previous video still applies here. We can compute the residual sum of squares, the RMSE, the R square. All that still makes sense here, is meaningful. But if you think about it, we should start accounting for a possible case of overfitting. We should take into account the complexity of the model. Why? Because as we saw in the previous videos, just by adding more and more and more variables to the model, we might allow the model to perfectly fit the data and still be a very bad model of reality because it would be overfitting our data. And so somehow we should start caring for the model complexity. So do we have a coefficient that puts on the one hand how good the model is, and on the other hand how complex the model is to try and see what the trade-off is? We do. The adjusted coefficient of determination, or adjusted R square, that looks exactly like the R square, but now it incorporates the second term that has on the one hand the amount of data and the number of predictors, P. So if we have a very large number of predictors, then this R square adjusted is going to be lower than the R square because it's penalizing for high number of parameters. And so it's kind of correcting in a certain way the spurious increase in the R square that results by just adding more and more and more and more predictors. And if we take a closer look at this term, if the number of observations is a lot larger than the number of predictors, then this thing turns into 1 basically, and in the end what we have is the R square anyway. So we have a very, very, very large data set then we're essentially looking at the R-squared. It's the same thing, unless we have a very high P. So in summary, if what we build the model for is predictions, if what we care about is how good the predictions are, then we should probably be looking into the RMSE, how well the model makes those predictions in terms of the deviations from the true value given the estimate. And if what we care about is properly understanding the underlying process, the process that generates the data, then probably we're going to start adding more and more variables to try and model that complex reality. And we should account for that model complexity into the goodness of fit. So we should be looking into the adjusted R-squared.